We're starting section 3.2, and that's the derivative as a function. First, we discussed the derivative function, then we discussed notation of derivatives, mainly two different notations for derivatives, and then we discussed derivative rules for power rule, constant multiple rule, and sum and difference rules, and derivative of a natural exponential function. And then we discussed the definition of E. So far we've discussed this, the fact that basically the derivative of a function y equal to f of x at x equal to a is, if it exists, is f prime of a, and it's the limit of basically f of x minus f of a over x minus a as x approaches a. Or it's f limits of f of a plus h minus f of a over h as h approaches 0. Either one of the definitions we use. And it's the also it's the slope of the tangent line, and it's the limit of slope of the secant line as the 2 point gets closer and closer to each other. Now, what we're doing here, and here we found f prime of a, right? F prime of a is for any a that is part of the domain, basically, and part of that f prime exists on that a value. Now, what you want to do is, because this is for any general point where the derivative exists, you want to kind of make it into an x. And so let's start with that. And then if I change a to x, I still have, see, all the a's change to x. Now it looks more like the functions that you know. And so it's the input x, the output is the f prime of x. So let's do an example. For example, for function f of x equal to x squared plus 4, if you write this definition, you get x plus h to power 2 plus 8 plus 4 minus x squared plus 4 divided by h. Now, if you, again, every time you write the limit definition, if the derivative exists, it will be a 0 over 0. In here, I realize that if the numerator is a polynomial, so it should have a linear factor that is 0. And the linear factor should be h minus 0, and that's h. And so I'm going to look for that. And how do I look for that? By, let's expand x plus h to power 2, and we get x squared plus 2xh plus h squared, plus, and the 4 over here, minus x squared plus 4. Two terms simplify, you end up with 2xh plus h squared divided by h, and then factor out that h that you were trying to, that was bothering you, and so you basically end up with 2x plus h. And now I can plug in h equal to 0 because it's not an indeterminate form, and I get 2x. And that's the derivative of x squared plus 4. So we're in, before getting into business of finding the rules, let's talk about notation for derivative. Let's let have y equal to f of x be a differentiable function. I want to talk about Lagrange and Leibniz. So Lagrange and Leibniz notation. So Lagrange notation is what we're using so far. It's y prime of x equal to f prime of x, basically. Leibniz, it's actually, there is a lot of merits in using the Leibniz notation. And we have to be very fluent using this. The only merit over Lagrange notation is that it's simpler. So when we know what is the input variable, and we know more, we use the Lagrange notation. But overall, Leibniz notation has a lot more merits. So what is the Leibniz notation? So you want to specify what's the input variable that you're taking the derivative of. So you write d over dx of f of x. That means derivative of f of x with respect to x. So it's derivative of f of x with respect to x. Or dy over dx, and that's derivative of y with respect to x. It reads that way. Or derivative of f with respect to x. And these are without the input parentheses. That one has the input parentheses. This one doesn't have the input parentheses on it. So derivative at a for Lagrange notation is f prime of a. For Leibniz notation, it's derivative of f of x with respect to x. And then this long line, that means evaluated at x equal to a. So here you, again, simplicity of Lagrange helps us. If you know what the input variable is, this is very simple. But not usually, it's not usually common when things get a little bit more complex to use basically that notation, because you want to have all the information in there. Namely, if you're using more than one input variables, or you're doing composition of functions, or a lot of other examples come in, you want to have that basically what you're taking derivative respect to right there. And sometimes it's actually easier to write the long line, which means evaluate it, and then x equal to a. Now over here, the other way to write it is derivative of y with respect to x. The big line is evaluated at x equal to a. So these are, and we have to be comfortable with all of those. So for higher derivative, if you're taking derivative twice with the Lagrange notation, you write double prime of x. If you take it, because we just defined that the function, there's a derivative function, and so we can take one derivative, then second derivative, then third derivative right there. After after a while, the primes become too many, and so usually after 3 primes, people start to put a little parentheses on top with an n. Do you know why there's a little parentheses? Because otherwise it looks like f to power n. But when you put the little parentheses, it means that derivative, nth derivative of x. That means you take the derivative once, twice, 3 times, all the way to nth derivative. And so in here, when you're trying to do a second derivative, that means you take derivative of f of x once. See, the inner part is derivative of f of x once, derivative of f of x with respect to x. And then you can take the derivative of that one more time. That's the second derivative. And or the other way of saying that is you take the derivative of y with respect to x, and you take the derivative of this new function, the derivative function, with respect to x another time. So the notation for that is d to power 2 of y over dx to power 2. And this doesn't mean derivative with respect to x squared. It's just when you have d2 up there, notation wise, it's easier to put it's the second time you're taking derivative with respect to x as this way. And so when you're talking about nth derivative, means take the derivative once, twice, 3 times, all the way to nth times of f of x with respect to x. Then that notation is d to power n y over dx to power n, and it doesn't mean derivative with respect to xn, it just means derivative with respect to x and